Hello students, let's go to next topic of our syllabus. So here the next topic is what optical path. So for this optical path, let us consider the light wave having a frequency, angular frequency omega and the wave vector k traveling in a vacuum. The phase difference between them can be given by one simple equation as it is nothing but what, as already we have learned that initially also, kx minus omega t, because these waves are moving along x-axis in a vacuum. So the having the k as a wave vector, omega is angular frequency, so this would be the phase difference between the wave traveling in a vacuum. Now the question comes here. Here the wave vector is nothing but what, the wave vector is a parameter which is related to that of the velocities and frequency by equation, where this k equal to omega divided by v. That is the point to remember. That is wave vector related to angular frequency and the velocity. So omega divided by v. Suppose the light wave travel a distance delta x. Light wave travel a distance delta x. So they will travel a distance delta x, distance traveled by the light wave. Okay, for this delta x distance travel in a vacuum, what the phase difference they have, that we have to calculate. The phase difference becomes, this is the distance delta x travel, so phase difference of the wave is given by delta phi equal to k into delta x. This would be the phase difference if light wave travel a distance delta x in the vacuum. That this is distance traveled, this is the phase difference delta phi. Okay, in a vacuum. But suppose these waves are nothing but what, as we know, just already we have just done k equal to what, omega by v. So we can write it here. So we can write further this as delta x into omega divided by v. So same equation can be written as delta x into omega divided by v. If the wave is traveling in a vacuum, in general this is travel in medium. So delta x distance travel in a medium whose velocity is v. This would be the phase difference. If this is in medium, so I will let here it is in medium. Any medium we have taken and that wave is travel by distance delta x, then the phase difference is given by this formula. Now suppose wave is traveling in a vacuum. Now if the wave is travel in a vacuum by again the same distance delta x, distance traveled in a vacuum, what we get here, we should get here phase difference as we get as delta phi equal to k delta x equal to delta x into omega divided by c. Now v is the velocity in the medium, c is the velocity of that light in a vacuum. That's why we have taken here it is c. Now let us consider same thing. We have to consider the medium. Suppose medium is there whose refractive index is n. So it has a refractive index of the medium is n, and wave is traveling, light wave is traveling in that medium whose refractive index is m. Then the wave vector for that medium, wave vector up till now we have assumed it as a k, here it is k dash. Wave vector of that medium is k dash, refractive index is a small n. In that medium, suppose the wave is traveling, what is the phase difference? So the medium, again here it is a medium having refractive index n and the phase vector is k dash. If it will travel a distance delta x, distance traveled by the wave, what is the phase difference? That phase difference we have to calculate delta phi dash. It is dash. For that medium we have assumed it as a delta phi dash equal to what? K dash into delta x. What is the k dash now? K dash here you should take a velocity basically. Now that velocity we have to consider in terms of what? That velocity in terms of wave. So k dash equal to delta x here as it is into omega divided by v, as omega divided by v. But here if you remember in 11th standard we have remember the relation v equal to what? There is one formula, v equal to c by n. So that put value here, we can write here delta x into omega divided by c by n. N is nothing but a refractive index, we can say c by n. So we get this equation. So we can write this as delta x into c into omega, sorry, delta x into c naught, it's an n goes to numerator, n into omega divided by c. So this equation we get. So here delta x omega by c, delta x omega by c, it remains same delta phi, only here n comes extra. N means what? Refractive index comes here in this equation. The new term comes refractive index. Now here, suppose if you put the value delta x dash equal to n into delta x, this if you put as delta x dash, then we can write this as delta x dash into omega by c. Delta x dash into omega by c, where or we can write here delta x dash equal to what? Delta x into n. So that value we have put it here and we get this equation. Now what exactly optical path is? In this case, suppose the wave travel a distance delta x, in any medium, or suppose it will travel a distance delta x in a medium whose refractive index is n and k dash is the wave vector. Okay, any wave travel in a medium whose refractive index n, the wave vector is k dash, travel distance delta x. If the same light were travel in a vacuum, to make a same phase difference, then it is said to be optical path. And that optical path is nothing but represented by n into delta x. This term n into delta x itself represents the optical path. If here n equal to 1, delta x and delta x dash are same, means in a medium and in vacuum distance travel would be same. Same thing can be explained in different way, and that is a better way to understand. This is as they have given in a book, we have just revised it. Now the better way to understand the same concept was given in terms of some equations, and that equations are easier than this one. Let's see what the equations they have taken further. So for further equation, what this is, now optical path in a medium can also be defined as corresponding path in a vacuum that a light travel in the same time as it takes in a given medium. So it is nothing but what? Optical path in a medium can also define as corresponding path, means distance travel in a vacuum as that of the medium in same time. So you can write here time. Time, as we know, time is nothing but what? Distance travel divided by velocity, or we can say speed. Velocity divided by speed, it will give the distance. And as there are two mediums, so we can write this as t equal to distance, suppose represented by d, and speed represented by v. So d divided by v. This is for medium, so I will write here medium. In certain medium it is moving, so it is medium correspond to distance in the medium, velocity or speed in the medium. Similarly, it is what equal to d divided by v in vacuum. So it is in vacuum, so I will write here suffix as vacuum. Distance travel in vacuum divided by same velocity of the wave in a vacuum. Now what is the optical path? Optical path means what? In a vacuum the distance travel. So we can write here optical path equal to d vacuum equal to this v vacuum divided by v medium into d medium. So just take these two equations and solve it for d vacuum, we get this equation. Velocity in the vacuum to the velocity in the medium into distance travel in the medium, that will give the distance travel in a vacuum, and that itself is said to be optical path. So this is the equation how they will find out the optical path. But we know velocity of wave in a vacuum to the velocity of the same wave in a medium, that will give the refractive index. So it will be n into d medium. So it will give the new formulation, that is nothing but n into d medium. So distance traveled by in a medium of refractive index n introduce in path difference of, so here this is in a vacuum, in medium it is n, so we can write here it is path difference, path difference equal nd minus n is common. So we can take this, sorry, nd minus d it is not nd minus nd minus d. Here d is common, in the bracket it is n minus 1. This would be the path difference that we can find out. So here this is nothing but, in short, it is the optical path. Now let's go to next topic of our syllabus, that is nothing but diffraction of light. What exactly diffraction of light means, that we have to learn. Okay, diffraction of light. So I will start with here the next topic of the syllabus, diffraction. Let's start with here, diffraction. Diffraction of light. So it is one of the phenomenon of light similar to interference. We have seen interference of light is one of the phenomenon. Similarly here, diffraction of light is another phenomenon related to light. What exactly diffraction means, that we have to see. So we know that in suppose some cases when the light incident on some obstacle, opaque object is there, just like this. On this object is opaque, it is not transparent to light. On this, when light get incident, it is seen that light get diffracted at the edges of obstacle, at this edge, at the bottom, or at this edges, this side of edges, this side or this side edges. Light get diffracted, it get bent and enter into geometrical shadow of this object, enter into geometrical shadow of this object, and that phenomenon of bending of light at edges of that phenomenon of light, that is said to bending of light wave at the edges of obstacle, is said to be diffraction of light. Bending of light at the edges of obstacle is said to be the diffraction of light. But remember, while doing this, the size of obstacle matters. The size of obstacle must be comparable to that of the wavelength of incident light. Whatever the light is incident on this obstacle, the size of obstacle must be equal to incident wavelength of the light. Then and only then light get bent and it enters into geometrical shadow, or we can say diffraction pattern can be observed. Now here in diffraction phenomenon, it is also applicable to sound waves. Okay, diffraction phenomenon is applicable to sound wave also. So wavelength of sound wave are larger, so diffraction of sound is easier to observe. See, light has very lower value of wavelength, so it is quite difficult to observe the diffraction in light. But in case of sound has a larger value of wavelength. For sound waves, its wavelength is large. That's why it is very easy to obtain the diffraction phenomenon in sound. Similarly, it will occur in light. Now let's go further. As there are two types of diffraction patterns. So there is one is said to Fresnel and Fraunhofer. So write down the first one, Fraunhofer. Fraunhofer diffraction. Fraunhofer diffraction, and second is said to be Fresnel diffraction. So there are two types of diffraction pattern. One is said to be Fraunhofer diffraction pattern, other is said to be the Fresnel diffraction. What is the difference between these two? That we have to learn now. If the source of light, slit, and this is nothing but the screen. So this is screen, this is a slit, and this is the source. If the distance between source and the slit and the screen is very large, the distance between source, slit and the screen is very large, it may be infinity, then that type of diffraction pattern is said to be Fraunhofer diffraction pattern. In Fraunhofer diffraction pattern, the wavefront uses nothing but what? Plane wavefront. Mostly as distance is very large, so when the wave comes, small part incident here and it comes to be plane wavefront. So the plane wavefronts are there in case of Fraunhofer diffraction. Wavefronts are plane wavefront, and these are nothing but such type of diffraction is said to Fraunhofer diffraction pattern. Now apart from this, what is my Fresnel diffraction? If the distance between source, slit and screen is not infinite, it is at finite distance, it is at finite distance, then that diffraction pattern is said to be Fresnel diffraction pattern. As the distance is very small, the wavefront used is not a plane wavefront. It may be cylindrical wavefront or it may be spherical wavefront used in a Fresnel diffraction pattern. Now let's go to experimental setup of Fraunhofer diffraction pattern, and let's see how the Fraunhofer diffraction pattern get observed on the screen. That we have to learn. So Fraunhofer diffraction we are going to learn only. Fresnel diffraction pattern is not in your syllabus. So let's start with the Fraunhofer diffraction pattern only. So let's start with this. So I have drawn here two diagrams. So first of all, let's see, both diagrams are same. How they are same, that we will see later on. First of all of you must concentrate on the upper diagram. So let's start with the experimental setup for Fraunhofer diffraction. So how the experimental setup was done for Fraunhofer diffraction pattern, that we have to learn. Here there are two lenses are used. Two lenses are used. There is one source of light. Basically, it is very far away from the slit. Source of light very far away from the slit. When the light wave coming from the source incident on this lens y dash, biconvex lens y dash, it gets splitted and it gets incident on the another biconvex lens mn, another biconvex lens mn. Then it is seen that, so as it will form, the second biconvex lens form images on the screen must be kept at a distance of focal length of this lens mn, so that we can observe here the 2 points P and P0. If you consider the point P0, it is obtained due to single light waves coming like this, directly they are coming from the source, or that we can say coming from y dash, the light wave comes and they will form a point on the screen, that is P0 here. What about P? P is a point that get formed here when the light waves are coming from the lens y dash here. What will occur at certain angular distance, another light wave get emitted. Suppose this is theta, this is also theta, then all this angle becomes same, they are at theta. So see, this light ray coming at an angular displacement theta, this goes straight line, it will form P0, and all the light ray which goes by the angular displacement theta, that goes to the point P, that goes to the point P. So point P0 is definitely the bright point. Why it is bright point? Because phase difference. See, so the first line goes straight here, because and from the center of biconvex lens any light ray are passing, there is no deviation to them, so it goes straight line. So light rays coming in upward and downward direction, they come in phase, or there is zero path difference. If path difference is zero, the point is said to be bright point. Now point P may be the bright, may be the dark, and that we have to find out a condition for brightness of the point P. We have to find out condition, just like interference we have done at point P, when it becomes minimum intensity, when it becomes maximum intensity. For that we have to find out a condition in case of diffraction pattern. Okay, now for that, the same experimental setup just I have drawn here at the bottom diagram. So if you see this second diagram at the bottom, it is same experimental setup as that of above one, only difference is what? I have removed this y dash mirror, this part I have removed, we get this diagram. Just if you skip this part, if you just erase this y dash like this, now whatever the diagram we are getting here, and that diagram is exactly similar to this one, I have drawn it here. So both the diagrams are same now. So just why we have drawn it like this? Because as we know, the Fraunhofer diffraction distance between source and the slit is infinity. So that distance is infinity, and that lens we can observe that particular diffraction pattern on the screen by just taking one biconvex lens. Just incident light comes, incident on the biconvex lens, we get a two or more than two the bright and dark points on the screen. So let's start with this. Let us suppose here AB, this is a plane wavefront. AB, this is a plane wavefront, incident on the lens like this. Plane wavefront AB. AB is a plane wavefront, incident here. Now when the light ray coming from A to P0, AP0 to BP0, they are coming in the phase, or we can say path difference is 0. So if we do AP0 minus BP0, it comes to be 0. If it comes to be 0, then what does it means? Path difference is 0, means the point P0 merge with the bright intensity point, and that is said to be central maxima. It is said to be central maximum intensity point in the diffraction pattern, that is said to be central maxima point. Apart from this, if the another light ray deviated by an angle theta to the normal, this P0, if they are deviated by angle theta in upward direction, then all light ray AP and the another one is BP. If you observe it here, AP, A to P and B to P, they are not in same phase. The path difference is not 0. There is some path difference. If there is some path difference, point P may be bright point, may be dark point. That is said to be secondary maxima or secondary minima get formed at point P. Now there are some conditions. when there should be secondary maxima, when there should be a secondary minima. That conditions we have to find out. Now here let us consider, suppose I have drawn perpendicular from point A. I have drawn perpendicular from point A on the line here, and that will reach to this bottom at a point C. This is the perpendicular drawn. So I have drawn this as a perpendicular to this part, this line. Okay, this light rays are there. I have drawn perpendicular, so it will touch it to here at a point C, suppose. And exactly in between A and B, exactly at the central part is suppose the point O. So this is the point O, exactly central part of this Nantabu. Exactly at the center part of this, the point O would be there. Is that clear? Now suppose this AB is a plane wavefront whose width is A. Now we have considered point O exactly at the middle. So this would be A by 2. This remaining would be A by 2. That's why I have written here A by 2, A by 2. Is that clear? Now the light ray which are coming with an inclination theta to the horizontal light waves, they will reach to the point P. Now point P may be the bright point or maybe the dark point, that we have to find out. Now here this lens we have kept so that we get here on the screen the interference pattern. So this screen must be kept at distance equal to focal length of the lens. Then and only then you get a well distinct interference pattern, otherwise you can't visualize the pattern. That's why this distance, focal length f equal to d, I have put it here. And here the distance from the slit or plane wavefront to the screen is capital D, and that is very much greater than the aperture of an plane wavefront. So that I have used here the word, the A is very much less than D. This distance is larger than this plane wavefront. That is the meaning of this. Now we have to find out some conditions here when the point P would be the dark intensity point, or we can say minimum intensity point, and the maximum intensity point get occurred when, that we have to find out. Let us consider for this, if we consider same diagram again, if we draw this perpendicular, I have drawn already here. If we draw the perpendicular on this, and beyond this point C and beyond this point A, right side, beyond point A and C to right hand side, if we consider AP and CP, this AP and this is CP. And now if you find out path difference, it come to be 0. Just you can look at in the diagram, AP and CP, the path difference come to be 0 because these two distances are equal. If the two distances are equal, the path difference definitely 0. So what is remaining part? This BC is remaining. We have skipped BC. We have started from point A to right side, C to right side. The path difference is 0. But when you want to find out path difference between AP and BP, the ray AP and the ray BP, we want to find out path difference. That path difference comes to be BC. And that we have to find out. If this is theta, this must be theta. Find out sine of theta in this triangle ABC. Sine of theta we have to find out. Sine of theta, opposite side is BC divided by hypotenuse. Okay, BC divided by hypotenuse. So it is BC divided by hypotenuse is nothing but A. So this implies that what is the value of BC? BC equal to A sine of theta, and this BC equal to A sine theta, that is nothing but a path difference between the two waves. One is coming from A to P, other is coming from A to P and B to P. Path difference is BC, and that path difference we have find out. BC equal to A sine of theta. That path difference we have find out. BC equal to A sine theta. Let us consider it is equal to lambda, suppose. Okay. Then here this point P is having a minimum intensity point. If it is having a minimum intensity point, what does it means? It is a dark point. Minimum intensity, or we can say it as secondary minima. Now let's go again. Let us consider point K. Here it is point O. Here this is the point K. Okay. If this is BC, OK must be half of the BC. Now we assume that BC equal to lambda. So OK equal to what? This distance OK equal to half of lambda, means it is lambda by 2. It must come to be lambda by 2. Now if we solve it again and if we apply the conditions again here, again point P comes to be the minimum intensity point, that is said to be dark point. So in general we can say when there is a path difference of 1 lambda, 2 lambda, 3 lambda, so on up to, in general, up to n lambda. Whenever the path difference between the two waves arriving at a point P is 1 lambda, 2 lambda, 3 lambda, so on up to n lambda, it is seen that point P has a minimum intensity, or we can say it is a dark point said to be secondary minima or said to be secondary dark points. So this is a condition. Path difference must be integral multiple of lambda. Now if you observe this and if you compare this with the interference pattern, then you can say that this is a condition for, in interference, this condition for maxima. Here it is the condition for secondary minima or dark point. So that is the difference you should remember. The condition gets shifted now. Just we have to remember that point. Don't confuse. In diffraction pattern, when the path difference is integral multiple of lambda, the point is said to be dark point, or we can say secondary minimum intensity point. But in interference pattern, it is exactly opposite. Okay, so that point you should take into consideration. So for in some same way for nth point, nth dark point, similarly for nth dark point, what are the conditions that we have to write? Nth dark point, we can write here a sine theta, this is the path difference, a sine theta equal to n plus minus n lambda. Now the question comes, why it is plus minus n lambda? It's very simple. If you go upward direction, it is plus. If you go in downward direction, it is minus. That's why it is plus minus n lambda. So this is a condition for nth dark point. Similarly, you can write a condition for perfectly bright point, condition for secondary bright points, and that is nothing but a, suppose in general, nth bright point. We can write a condition for nth bright point, and that is nothing but what? A sine theta equal to plus minus n plus 1 by 2 lambda. N plus 1 by 2 lambda. So integral multiple of lambda, here the condition it is n lambda, it is plus minus n plus 1 by 2 lambda. So here it is integral multiple, it becomes here odd multiple of lambda. Okay, so that is nothing but a condition for secondary bright points or maximum intensity point, secondary maxima. Bright point means it is secondary maxima, dark point means it is secondary minima. So that are the conditions that these two equations we have derived. Suppose this is equation 1 for condition for dark point, this is equation 2 condition for bright points. Now here, apart from this distance of secondary maxima and minima from central bright point, at what distance the secondary maxima get from, at what distance secondary minima get from, that we have to find out. For that we have to derive some equations in little bit. By using these two equations we are going to derive it. As we know, we have assumed that capital D, the distance of the screen from the slit, it is very much greater than small a. A is very small. That is width of plane wavefront is very small. AB width we have considered, it is very small as compared to distance from the slit to the screen. If it is A is very small, theta must be very small. If this is the condition, theta must be very small. If theta is very small, we can write sine theta must be nearly equal to theta, and that is nearly equal to tan theta. Sine theta must be nearly equal to theta, that must be nearly equal to tan of theta. Okay, so if that will go on, just find out from the figure what is tan theta here. If you find out from this figure what is tan of theta in this diagram, in this triangle, if you find tan of theta, opposite side divided by adjacent side. Opposite side means what? PP0. Let us consider this is y. Opposite side is y. PP0 is opposite side, that is y. Adjacent side is nothing but OP0, that is D. So we can say that is nothing but what? PP0, that both all tan theta, if you find out, it comes to be PP0 divided by OP0. But PP0 is nothing but what? It is y, and OP0 is D. So we get here theta equal to y divided by D, and that is nothing but we have find out the condition angular displacement would be very small, and that is equal to y divided by D. Now suppose There are bright and dark point whose value of y, distance from the central bright point for that is y d dark point, nth dark point suppose, so it is y and d for nth dark point, and here it is y and b, it is nth bright point, distance of nth bright point, or they have just used small d and small b, so I will use small b and small d. Y and d means what? Nth dark point, distance of nth dark point from the central maxima. Y and b is what? Distance of nth bright point from the central maxima. Let's look at here. So this is bright point. This is y and d means what? Nth dark point distance. Y and b means what? Nth bright point distance from the central maxima. And that we have considered and we have written here that values. But we know the values of that are nothing but what? Values as we have learned here. Just conditions we have done. A sine theta equal to plus minus m lambda, but theta is very small, so a theta equal to n lambda. Condition for dark point, for this dark point, so we can write here, just I will make here two columns, and here y and b, bright and dark, so just make two columns. Okay, so for dark point what we get? A theta, sine theta is theta na, so equal to plus minus n lambda, equal to plus minus n lambda. Find out theta. Theta equal to n lambda divided by a. So it is plus minus n lambda by a, that is theta. But what theta we get here? Y by d. We get here this is y by d. So you can write here it is y and d divided by capital D. And our aim is to find this distance y and d from the central maxima, find it out. So this equation implies that y, distance from nth dark point from the central maxima, is equal to plus minus n lambda, this d goes to numerator, divided by a. So this is the distance of nth dark point from the central maxima. Similarly, use this equation, this equation for bright point and find out the y and b. So we can write here again theta equal to plus minus n plus 1 by 2 lambda divided by a. That is for according to the second equation. I have written that is equation for bright point. Now here what is theta? Y by d. Y and b divided by d. It is capital D, sorry. It must be capital D. Y and b divided by capital D. So I have written y and b divided by capital D. Our aim is to find out y and b. This implies that distance of the nth bright point from central maxima equal to n plus 1 by 2, d goes to numerator, lambda d divided by a. This formula gives the distance of nth bright point from the central maxima. Now remember, this will give the equation for central maxima, and here if we consider lambda d by a, lambda d by a, it is said to be width of central maxima. Lambda d by a, this is width of central maxima, so you can add n plus 1 by 2, and that width was represented by w, so we can write this as w. Similarly, initial equation, this equation we can write this as plus minus, or simply here also plus minus, here is n lambda d by a, so this term is nothing but what? W. So nw, n into width of the central maxima, half width of the central maxima. So this is nothing but a condition for secondary maximum intensity point. These are the condition. Secondary minimum intensity or dark point, these are the condition. Dark point and the bright point. So we have find out these conditions. Now what exactly width of central maxima? So see, width of central maxima we have to find out. So in that case, width of central maxima, so width of central maxima. Width of central maxima means what? At P0 we get a central maximum intensity point among all at P0. Okay, and what should be the width of that P0? That we have to find out, and that width comes to be double. Double means what? The W is the width to left side or up side, and W is the width to bottom side. So I will show it here in the diagram. If you consider here this diagram, if you consider this P0 is here, okay, center point, central maxima, up to this, here it is W width, upward and W width in downward. So this total would be the width of central maxima. That would be what? W plus W is twice W. So that we have to find out. As we know W equal to lambda D divided by A. So width of central maxima equal to twice W, it is 2 lambda D divided by A, and that is said to be width of central maxima of the in diffraction pattern. Now let's go to the next topic of the syllabus, as they have mentioned comparison of Young's double slit interference pattern and single slit diffraction pattern. In Young's experiment there are two slits, S1 S2. Diffraction there is single slit. What is the difference between them? That we have to learn. So just see what they have done. In Young's double slit experiment, the slits are very much thinner than their separation. Small d is the distance between S1 S2, and the slits are very much smaller than that distance d in case of Young's double slit experiment. Apart from this, usually they can obtain this parameter either by using biprism or Lyod's mirror. Lyod's mirror that we have seen, biprism experiment also we have seen to obtain that particular pattern in double slit experiment. Separation between slit is of the order of few millimeter. Very few millimeter. The S1 and S2 are separated by very small distance. The best possible setup, we can easily get 30 to 40 equally spaced bright and dark fringes nearly of the same brightness on the screen in case of double slit experiment given by the Young. What will occur in case of diffraction of single slit experiment? Usually width of the plane wavefront is less than 1 millimeter, and it will be taken on either side. We can see around 20 to 30 fringes of the central maxima, with the central maxima being a brightest point in diffraction pattern, and bright fringe is twice, the intensity is double than that remaining secondary maxima point. That is the only difference between these two. And further, in your book they have given a table 7.1 that will give the difference between interference and diffraction pattern. They have given for another bright point and another dark point, they have given some physical parameters. In case of double slit experiment, double slit means what? It is interference, and single slit diffraction pattern means it is for diffraction. They have given the changes, so you must remember all the changes. Just go through this table and try to remember this table, try to learn this table, because this is very important. That will give the difference between interference and diffraction. Apart from that, below this table there is one equation 7.16 in your book. I am not going to draw it here. So in that diagram, what they have shown, intensity distribution in Young's double slit interference and single slit diffraction interference and double slit diffraction they have shown. What the difference they have given, that I will try to draw it here in short. In Young's double slit experiment, the intensity is supposed taken along y-axis. This is intensity, so they have drawn it like this. Such type of thing they have drawn. The intensity is throughout the same. In case of Young's double slit experiment means what? It is Young's double slit experiment means it is in interference. The intensity remains constant. In case of what? Diffraction, single slit diffraction, what they have shown, intensity they have shown like this. Same thing, they have drawn it like this, and they have shown the intensity varies like this. So this is central maxima, again the central minimas are there. So this would be the pattern, okay, such type of pattern. So this is central maxima, this is W to this side, W to this side. This secondary maximas, this is first minima, this is first minimum right, first minimum right, left. So here intensity is continuously changing. Intensity here is continuously changing in case of diffraction. This is W to right side, this is W to left side. That's why we have taken twice W as the width of central maxima, W plus W. So this is central maxima, first minima to right side, first minima to left side, first secondary maxima to right, first secondary maxima to left. That's why. So from these two we can say, in case of interference, intensity is throughout constant. In case of diffraction, intensity changes here, and that is the difference only. Now after that, in this the next topics are also there. They have mentioned resolving powers and some other things, but that topics in this year, that was that was reduced in this year. That's why the next remaining topics are reduced in for this year due to academic the COVID pandemic. That's why we are not going to take that topics. So in this fashion, we have completed this chapter, and next period we start with chapter electrostatics. So try to watch my video first. Watch my video, then try to read the same topic from the book. Definitely, you get a better understanding of that particular topic. Still, if you have the problem, you can contact. Okay. Thank you very much. See you in next video with the next chapter electrostatics.